Okay, so as I said, the last lecture on clustering on data types, which is just a small extension of what we have done. We are skipping that at least for now, and then we are moving on to the next phase of the course. Okay, and this phase is about what you call simulation, and there's something not mentioned here about queuing systems. So simulation is a general tool which is applied in many situations. So we are focusing on what you call the queuing systems, simulation of queuing systems. So we'll not only be just looking at simulation only, but queuing system from theoretical perspective a little bit. So normally what we do is we do this lecture, and then we go to queuing and then come back to simulation. But this time I'll be doing it slightly differently based on previous experiences. I'll be covering half of this lecture, inshallah today, whatever days. Then I'll go to queuing and then we'll come back to simulation. Why is that? Because many concepts that will come after where I stop actually are coming from the queuing theory. Okay, so sometimes I have to like roughly explain and then later we talk about that, right? So I think it is better that we talk about basics of simulation and then go to queuing theory, learn whatever we needed to learn there, come back so that when we start discussing about simulating the queuing systems, you're already aware of those concepts. Okay, you're all okay with that? So we'll be making a little back and forth switch between the slides. Slide means this slide, I've uploaded two sets of slides. Okay, one is called 10 and 11 simulation intro, and the other one is queuing, right? So today we'll just kind of cover 15-16 slides of this simulation, and then inshallah we'll next class we'll be covering the queuing, and then we'll come back to this, and we'll just continue from there. The rest of the slides are all not just slides. I mean the rest of the semester, inshallah, we'll be talking about simulation. So simulation is a term that I'm expecting that at least you may have heard about this term before, right? Like where? Like in games? Yes. Have you played games like Need for Speed and these kinds of things? No, not interested. This is like the interested boys are interested in those games. I can't think of a simulation game in which girls are interested. Minecraft or maybe these kinds of things. I don't know. This is for a younger generation. Okay, let's just at least But what is peculiar about simulation? When you see something and you say that this is simulation or simulation game or something about simulation, so what notion or what concept comes to your mind? Okay, so somehow what I understand from you is anybody else would like to give an input to that? Yeah, so I think you may have at least some idea about it, right? So there's a reality, and would like to recreate this reality on computer screen, right? So the basic idea is essentially the same. It is about recreating the reality on screen. The real question for us from business perspective is not about whether we can. Yes, we can. The question is why we would want to do that, right? It's not just about fun like in games. We wanted to do it because we wanted to achieve something. That's what we really needed to understand even before learning simulation. People learn simulation, but they don't have a clue why they are doing it. It's all in the purpose. If you understand the purpose, you know when I need simulation to use. Okay, so it's about the purpose that we must understand. So I think you kind of answered the first question already. What is simulation? So it is about, somebody mentioned about imitation here. So it is about imitating, the real world. And because we're dealing with businesses and so on, so we kind of throw in formal word, but it does not have to be there. imitating the operations of real world processes or systems. Now, one of the keywords that you'll see here is, normally simulation is dealt with when you face a dynamic situation, things that are changing over time, right? So this is one of the major business applications that where simulation is applied, where things are happening over time. So that's one feature, but not all features. There are a few more important things we need to keep in mind. But one of them is for sure that where scenarios are things are changing. Think of like ATM machine. A very simple example. And by the way, do you see a queue here? So we intentionally kept this picture here because there's a queue in there. So you can see that things are happening over time, right? People are coming, standing in a queue, taking the money. Some are taking longer, some are taking shorter time, right? And the queue is increasing, decreasing. Something is happening. As a business person, eventually we'll keep on going back to the business question. If I'm a bank, what am I concerned with here? In terms of for example, if I'm a bank and I see this queue, what would be the first question that should come to your mind? You think this queue looks good? Crowded. Long line. So what you should be thinking here? Hayat, questions like these, right? But can you answer this question just by looking at it, what's going on here? Do you think 2 is enough? Do you think 3 is enough? Lots of questions, right? Difficult questions to answer. If I try putting more meat and I say, okay, let me put 4 of them, and then it turns out that the 4th one is never used, what happens to my heavy investment? And I learned it the hard way after doing like 3 months project, and I spend a lot of money, right? So I'm just right now building up a case for simulation here. So it's a difficult prospect to deal with. Now, one of the things that makes this problem difficult, that inshallah we'll talk more in detail about, is what? No, just think even higher. Why this? Apparently, it's just a line, and we have to calculate some number of people in the queue, and then decide like how many ATMs to keep, right? Why is it looking like a more difficult prospect to deal with? Because do you think this line will always be like this? Not just change over time, but I need to hear a word. Can you even tell what the change will have? What is the change that will happen over time? Why can't you tell that right now it's this one, next hour it's this one, next? Because there's uncertainty in there, right? You cannot tell how it's going to behave. There's lots of randomness into it. Do you understand what the point I'm trying to make? Maybe next day I come, there is no queue at all. There goes your investment down the drain, right? It's a complex situation. And complexity is not just because of time, but we'll talk more about it. It is because of randomness in the system. There's lots of uncertainty we are dealing with, right? So, and of course, there are some other applications, because right now we're talking simulation in general. My background is engineering, so I keep bringing in that here. It's like an engine part, and we do a simulation called finite element method simulation, FEM simulation. It's not like this at all. There's nothing common between these two, except for the word simulation. But as we run this one, we can actually kind of identify, the software can identify the stresses in the parts. The stress means like the forces in the part, and you can see that these are like the regions which are more under stress. So as an engineer to design, we make sure that these parts are designed better than, for example, this is low stress area, this is high stress area. This is extremely high stress area. It means that the part can actually break from here, right? So rather than designing the part, putting it in the car, and the car, a lot of failures happen, we actually do it here on the screen. Test it, redesign it, test it, redesign it, test it, redesign it, test it, and then put it in the car. And the failure doesn't happen. Now, do you see the purpose of simulation? Now we send it to customers, 10,000 cars sold, and then it turns out that a part keep on breaking. And then you have to replace, you have to redesign, so much expensive. So you design, test, design, change, design, and then this is one purpose of simulation. Something happening here as well. Inshallah, we'll see. No randomness, but lots of randomness, but we can kind of do the same thing. We can recreate reality again and again on screen with very low cost, very far, less time, and so on. And then, of course, there could be other examples to it. So in business context, especially, simulation are essentially tools used for decision making. They support making better decisions. The queuing example I showed you, you don't need a simulation tool. If you want to make a decision, you can still make a decision. But if you want to make a better decision, then simulation can help you make better decision. I can still watch by my own eyes and say, let's add one more ATM machine there, right? One more teller machine there. So it's entirely, it kind of goes to, in the sense that it's a supportive tool. It will help you improve your decision making. And of course, simulation is not the only tool that is available to you. We have talked about optimization. You remember that? So optimization is actually a competing tool in many situations, but not always, but many times they are a competing tool. I'll come back to this in a second. So, how do you relate this simulation with mathematical models? Usually done on a computer with appropriate software. Simulation, just like we saw in Orange, simulation cannot be done by hand. There is no way you can do simulation. With so much numerical number processing, number crunching you have to do, you can never do it by hand. So what you'll be needing is a software, and of course you need normally a powerful computer. Now these laptops have already become powerful enough to at least to do basic simulation and so on. So it can help you in at least two different cases. As a descriptive tool, it can tell you what is going on better. That's like one thing where simulation helps, because in order to make a decision, the better you understand, even if you're making judgment-based decisions, you can still make a better call because you understand the problem better, right? So what is going on through what if question, what if that question, that is one thing. Then it can be used as a prescriptive tool. Prescriptive tool is where it lets you, the software kind of suggests you something. And this is like a good solution. Okay, so descriptive, prescriptive. By the way, the mathematical models are entirely serving this purpose. Of course they do that, but they're primarily, there's no comparison, there's no competition when it comes to mathematical models prescribing you the solution, best solution. Because when we talked about optimization, they guarantee you the best solution. The other techniques, they do not guarantee you the best solution. Okay, they can lead you to good solutions, but we have talked about that. But of course, simulation basically kind of deals with both. Now, one of the things where, because I told you that mathematics is superior to simulation, right? This is the case I'm making. So which one ideally I wanted to use? Eventually in business, I want better decision or I want the best decisions. So what should be my first choice? Mathematical models, right? But the problem with mathematical models is that in complex situations, they become very difficult to even create and very difficult to solve. And very quickly things become out of hand when it comes to mathematical models. So this is the point where you have to resort back to other tools. And this is where we are mentioning about simulations are normally applied to complex systems that are impossible to solve mathematically. Mathematically is, I wanted to go mathematical way, but maybe it's just too much to handle on mathematics level. I cannot even like create equations for that, too complex, right? So this is where you'll see simulation is very easy to deal with. Certainly, if you need this skill for mathematical models, like in terms of your people who are doing the project, simulation is far below that. A lot of people can handle simulation, but very, very few people are able to handle the mathematical complexity of these big systems. Okay, so you can see that even if I'm in a company, I'm unable to find a person who can deal with it mathematically. What can I do then? I'm unable to find the people because the skill level required is so high, right? So the fallback plan is simulation. Simulation will still do a good job for you. Okay. So, but we need to now ask what do we mean by complexity? Complexity is actually in different senses. Complexity could simply is coming out of the size of the problem. Too many variables, right? Too many variables. There are, we are doing something which requires thousands of things interacting with each other. This is one type of complexity. The underlying idea is not very complicated, but too many things talking to each other, and then it becomes difficult to manage. But there's another complexity, which is in the nature, like the one like in the example I showed you. In the queuing, it was simple, right? An ATM machine and a queue, but it became complicated because of randomness. It goes into the nature. So it's not just size. It has to do with the nature of the problem, or in real world, many times what you deal with is both the size issue and the nature issue, right? So it is both about the size and the nature. So we have built up a case for simulation, but as I told you that simulation can be of so many different types. We'll be focusing on a particular kind of a simulation, which is called discrete event simulation. It is because it is this type of simulation is able to deal with many business problems, especially the queuing problem that we are looking at. Okay, so yeah, does it make because we are now limiting ourselves to only discrete event simulation, is it going to limit our ability to facilitate business decision making? The answer is no. This still is such a huge area, and still is able to solve uncountable number of problems. So still the tool that you're going to learn today has huge applications. It's not something small. Although it's a type of simulation, but it is applied from manufacturing, bank operations, airport operations, transportation, logistics, hospitals, computer networks, business processes, chemical plants, fast food restaurants, supermarkets, theme parks, wherever, so it has huge application, the tool that you're using. So I think you can see that it's practically everywhere, right? So, so systems, facilities or processes, actual or planned, so basically not every aspect of it, but, as we'll see, it can be applied in various places of all these different areas. So one of the things, word that kept on popping up on the screen was system. So system, how do you define system? Did we talk about system? I think in project management, you may have heard about system. Anybody remember anything about system? What is a system? A simple definition of system. Yes, referring to that, input, process, output, right? So you have something that goes into something, right? A process, and it gives output. But there we talked about not just system, but a series of processes connected to each other. Input, process, output, the output becomes input to another process, right? So it's like, if you see things like that, you know, you're able to kind of model complicated systems. You need to start viewing things as a system where you have inputs, you have processes, you have outputs, and they are like connecting with each other. So a set of interacting components. This is where we are kind of looking at interacting component means like interacting component means we are talking about those processes, right? So they are now interacting with each other. Interacting where? Interacting through their output going becoming input to another one, right? And then you can always have multiple scenarios, right? You know, multiple an output going into multiple processes, and you know, different processes input going into output going as an input, and so on. So you can always you know, whatever problem you're facing, the system you're facing, you can convert that into something like this. So, and then you look at this definition, set of interacting components. Where is this word interaction coming from? Interaction, as I told you, is coming from here, how they are connected to each other. Connection, whether it could be connection in terms of information flow, or connection in terms of material flow, connection in terms of cash flow, right? Somewhere they are connected. Connecting means it could be even two, they can, you know, talking to each other. Interacting components or entities operating together to achieve a common goal. So now common goal is another important aspect of a system. When there are so many parts working together, they are eventually trying to achieve something together. Like in a hospital, you have so many, you know, departments, units, they are all talking to each other. Eventually they are trying to serve the community, right? So any people coming in with whatever problems so they are serving. Same thing goes with banks, same thing goes with universities and so on. So trying to achieve a common goal or goals. It could be multiple goals as well, of course. Systems such as the one on the previous slides are mostly complex in nature. I told you complexity comes from the size or the nature. So we are dealing with complex systems. Systems means something like this, where you have interacting components trying to achieve a common goal. Like here, you know, like a computer network, and you have network devices connected, computers connected, people working, and then, you know, they are interacting together to, even you can see banks in there and so on. The actual details of example are not important. What is important is you can identify different processes, the flows going in between, you can see from the arrows, and then that's how systems are working to achieve some common goal. Now, when you're dealing with a system, so in your projects, in the rest of the simulation, you need not to forget, you should never forget about this term called system. So we are dealing with complex systems. We are trying to make better decisions while dealing with what? Complex systems. Is that clear so far here? Yes. So our eventual aim is to learn simulation so that we can facilitate difficult decision making happening within a complex system. Right. So now since we know that we are dealing with complex systems and would like to use simulation, whatever. So what exactly are we trying to do? That's the question now. We'll try to make it more clear. Fine, there's a complex system in place, and there's something I have to do with it, you know, in terms of business decision making. But can I be more precise? Well, I can tell you that there are two major things that normally people try to address. And at the level I already mentioned about descriptive and prescriptive. Trying to find out what is going on and how something can happen. Right? You understand that? So again, think of descriptive and prescriptive, and it is coming here. So what is going on? I did not elaborated it earlier. So you might be asking questions like estimate performance of a system. Like think of this queuing example. I might want to go descriptive way. I might want to ask what is going on, and within what is going on, I wanted to ask tell me what is the performance of this unit here. So can you think of some way of evaluating the performance of that example, the bank ATM teller machine that I showed you? From the think of customer perspective, you go there. What do you expect to happen there? Quick service. So can't you just convert that into a performance measure, right? Maybe in terms of waiting times, average waiting time per person, right? Are you able to follow me? So number of customers in a queue at a time. Now we can create those measures, but we are now looking at this what. So this is one big question that normally simulation studies are used, but we don't have to be using simulation alone, but in general, one of the major problems that business people deal with is what is going on. Okay, and one of what do we mean by what is going on is to measure and estimate performance. And eventually our aim is to later improve performance, or even like I showed you in the engine example where failures can occur. I wanted to identify where failures can occur. Now, in terms of how we are going into the prescriptive, how we can solve a problem. First, we discovered that queue is too long. How can I solve this problem? So normally they come on one after the other. Okay. So the first level is what is going on, and the second level is how you can deal with it. Now, there are various ways to deal with it. Take the example of the car example, the car engine, as well as, although we are not dealing with engine problems, the business problems, or the queue. One way to deal with the bank teller machine and the car was to experiment with actual system. I change the design of the rod and see if it fails or not, hoping that it does not fail, right? Or in the bank teller machine, if I have like what goes in Albake, they have huge number of customers coming in, right? So they are like people standing. So they experiment. Let me keep one person, and then let me add one more person the other day. Then let me add maybe a third person, trying to serve people there. This is experimentation with the real actual system. Can you see the problem with experimenting with the real system? It's first of all, it's time consuming, hugely costly, and it's affecting your customers, and it has huge problems associated with it. So normally experimenting with real system does not happen a lot, except maybe in one last stage or something, like in a car crash or something. They don't build and crash the car like that. They actually have spent thousands of hours on computers before making the final test. Okay. Then some people say that in certain situations, not all situations, because actual testing on actual system is tricky. Tricky in the sense of time, in terms of cost, in terms of resources, in terms of losing goodwill of the customers, and many other things, right? So they say let's experiment on like a physical model, but physical model doesn't work all the time. Like in HCI, you can build a physical model, right? But not in a queuing system. What would you do when how would you make the customers come and so on, right? The third one is to develop and experiment with some mathematical, or I think better term is not mathematical approaches, but analytical approaches. And under analytical approaches, you have mathematical models and you have the simulation. Okay. And you know the difference now between the two. We have had a discussion that ideally would like to be mathematical because they are far more precise and they allow you to make the best decisions. But because of the complexity, we at least have an alternative. Not a weak alternative, but quite a powerful alternative. But certainly, when it comes to performance, mathematical models outperform. Now, while I say mathematical models are like the most outperforming one, many times to make them work, we actually have to do certain things to make them work, because they are already complicated, but we are keen in using mathematical models. So what we do is we try to make certain simplifications, certain level of what you call abstraction. Abstraction means like convert a concept into something abstract. I cannot think of an alternative word. You know the meaning of the word abstract? Abstract means something, a generalizable concept, not like very specific. So, and this means that while they are, because of those simplifications, you may run into the problem of making assumptions and approximations, which again is taking you away from the ideal, the optimal solution and so on. So, and of course, because of those assumptions, you may not be exactly duplicating, the real system. Like I don't know whether you have covered PERT by now, CPM and PERT in project management. Have you covered critical path method and program evaluation review technique for scheduling? What's the difference between the two? You have said yes, you need to tell me what's the fundamental difference between CPM and PERT. Sorry? I cannot hear you well. Which you do in both. Right? Let me make a quick recall. CPM, you have activities and you have predecessor relationships, right? And then you try to create a network, and then you try to find the critical path and the critical time. Now, are you following me? Now you do exactly the same in the PERT. What is the fundamental difference between the two? The fundamental difference is CPM deals with what you call deterministic systems, and PERT deals with with randomness, we call it stochastic systems. So the time in CPM, what you give is just a fixed time. In PERT, you say most likely, optimistic time, pessimistic time. Have you talked about that yet or not? Maybe not. Inshallah, you'll look at it. The point I'm trying to make here is, when you deal with CPM, you're assuming that an activity is taking 5 days. This activity is taking 7 days. Now, what you are implicitly doing is making an assumption. It will be finished in 5 days. It will be finished in 7 days. Now, it's an assumption. It may not be happening exactly like that. You may be taking 5.5 days. You may be taking like 4.8 days, right? Do you understand what I'm trying to say? The assumption thing that I'm trying to tell you. Many times in mathematical models, we make those simplification assumptions. When it's actually a random thing, we assume it to be what you call deterministic. Determinism is a term where there's no randomness. You know exactly what is going on. Okay? So we make assumptions like this, but we have to be reasonable that randomness is so small that we assume that there is no randomness, right? So, but if randomness is too big, then this becomes problematic. And of course, if the model is not simple enough, especially because we are talking about queuing models, you cannot create mathematical models, and then you have to only use the simulation to deal with. Okay, now let's try to think of a queuing system as queuing real world scenario as a system, as input, process, output, because that's how we need to be looking at it. So what do you see this scenario? What scenario do you see here? It's like a typical bank counter, for example. People are coming in, being served, and then they're leaving. So how can we visualize this as a system, as like a simple process? Is in process we need to have some inputs, we need to have some process, and we need to have some output. So the input goes in there is one set of input that goes into the system is what you call an operating policy. It means that are we allowing single queue? Are we allowing multiple queues? Are they single servers? Server means, people who are serving, or are they parallel servers? Are we allowing first in, first out? Like if you go to hospital in emergency, they don't use first in, first out. They use a queuing concept called priority queues. And sometimes you have first in, last out, depending upon the situation, right? So this is what you call, these are going in as an input. Then you have some, what you call input parameters, such as number of servers. Are they one, are they two, are they three, how many? And some more things that I'm not talking about it at the moment, but they are trying to capture the randomness. I told you that there's randomness into it and we have to deal with it. So randomness in time. We're trying to capture that randomness, and for that we have written here inter-arrival time. Inter-arrival time means the time between two customers. The time spent before the second customer arrives. So inter-arrival time. The word distribution here, we'll see later, it tries to capture the randomness. Service time, again, you go to the Panda and the Panini and Farm, whatever. Every time the person who's doing the checkout takes different time, right? So again, it's like random, you cannot predict. So server time distribution, again, distribution is a parameter. Then what is the output? The output are performance measures, for example, that we talked about, waiting times, system size, percentage utilization of the systems, and so on. So these are things. So because we are dealing with systems that have randomness into it, we call those systems stochastic systems, and we try to build stochastic system models or process models for it. So stochastic is just a word. Whenever you see the word stochastic, it means that there is some randomness into it. Okay, so it's just a term used equivalent for having randomness into it. So random and uncertainty is inherent into these things, and examples are like what we have seen. Bank with customers and tellers. So customers coming in and then they are being served, and some sort of queues are being formed. Now, I'll not try to confuse you too much, but there are different kinds of simulation. We are going back to different kind of simulation. One is called static Monte Carlo simulation. Have you ever heard about this term called Monte Carlo? You know about Monte Carlo? Yeah, so Monte Carlo is famous for so many things, but one of them is those games that people play with choice, not choice but with luck, right? So Meister, I'm talking about gambling. Yeah, I wanted to avoid using the term, but I still have to use it. So they see that they're dealing with chance. So because they're dealing with chance, so they started to think about how to deal with this randomness. And if you're dealing with randomness at a particular point in time, not over time, we use something called Monte Carlo simulation. In fact, in Python, in one of the years, one of the groups they actually you did EMD, right? So there they actually did Monte Carlo simulation. So Monte Carlo simulation is about, at one point of time you try to capture the uncertainty. But if it is over time, we use discrete event simulation, and we use what is called continuous simulation, which is mostly used in like engineering application, like water level in a dam. It is constantly changing, right? Something that continuously changing, we use this continuous simulation, but discrete event simulation. So now I think it's good time to kind of look at the name more carefully. The name I used was discrete event simulation. So if you see that in level in a dam constantly changing because it's like the water flow is happening. So what makes this distinct? It says discrete event. Discrete is opposite to continuous. It means that nothing is happening continuously. It's like something happens and it becomes stable. Something happens, so it's event based. An event happens and the system changes, and then it becomes stable. and then another event happens, and then it changes. So if you're talking about discrete events changing the system, that's what we are talking about. Now think of, again, queuing example. The system is now stable. Another customer comes in, that's an event, and that changes the system. Or a customer being served, the customer leaves, that's like an event happened, right? So we are talking about those discrete events which you can identify. And this is mostly applicable in queuing and inventory systems and so on. So how to simulate? Just like clustering, we can look at a few examples that can be done by hand, but we will not do it. There's no point doing it. It's not a purely simulation course. We are looking at it under the DSS course. And if you are having a simulation course, then you have to go deeper into it. But there's a famous example called Buffon needle and cross experiment, which there is in a book that typically people in simulation, they do it by hand. It's a very interesting one, but again, not within the scope. You can use Excel, but to very, very limited extent. You can do programming by yourself to simulate. But I think you can imagine that it might be extremely time consuming and difficult to deal with, because every time you program and for a single simulation, and that it doesn't, practically it's a very, very bad strategy. Just like Python, there are simulation languages dedicated to create simulation programs, and one of them, which is almost universally used everywhere, it's called Simon. Simon is a programming language, which means that very quickly you can create a short code and you can create a simulation program. But now even better, on top of Simon, people have created, just like in Orange, behind Orange is Python, right? But you are doing interactively, you're dragging and dropping components and so on. So people have developed a layer on top of it, visual layer, to allow visual programming, and there are software packages like Arena, and there are some other ones, but Arena is like dominating 80% of the market, simulation market. There are other software, but Arena, nobody comes close to Arena. So that's why we have picked Arena as a software, okay? It's a very easy to use software, just like Orange. And unlike you spend time 3 months programming, you can just get the same job done in 3 minutes. Maybe not 3 minutes, maybe half an hour, but you'll still be able to produce something like that in such a short time on Arena. Very, very powerful, very easy to use, and not a lot of skill required as compared to, like in programming. Say that again. Yes, we will. And this is one of the things I want you to do. Download and install Arena. I told you in the beginning to install Arena. If you have not installed Arena, then please do it now. The student version, the academic version rather, has full capability, except that the size of the problem is limited. Okay, so it does not say that you cannot use this part, this part, this part. You can use everything. The only restriction is, if your model becomes bigger than a certain size, then it says it does not allow you to save it. Okay, you can even create it, but you cannot save it, and you cannot run it. Okay, so inshallah, we'll be using, actually, just like Python, in terms of approach. What we will be doing is we'll learn. I'm going to show you a full path of conducting a simulation study. So because I'm going to show you this is how you conduct a simulation study end to end, we'll look at the first step, and I'll ask you to, we'll be starting project in the parallel. So if we have covered like part 1 in one class, let's say today, I'll ask you to now go and deal with that first step for your project. So you have to create groups now as well. Maybe you want to carry the same groups like before, it's fine. But then we are going to talk in detail about what does that mean, what do you expect to do in this first step, right? And then in that step, you go and you you finish that part. And then we'll learn the second step, you do that second step. For example, develop a conceptual model. So what does that mean? We identify the objectives, we do that. We then collect, the second step says collect data according to it. So we'll talk about how to collect data in Excel file, in papers, this particular data you have to collect. We'll go into details of it, right? You go and you collect with timers and whatever, you collect data, and then it says about, I showed you about interarrival time distribution and so on. So that step, when it comes, we'll say how to find that, we'll do that step and so on. We keep on doing that until the end. And Arena is just part of it, not the whole of it. Somewhere you have to develop the model on Arena, but before that, there are lots of things, and after that, there are a few things, okay? So I want Arena to be installed. We are not going to be using it immediately, but when we'll be using it, I'll let you know, and you have to bring your computers here because we need to learn how to use Arena as well. Okay, advantages of simulation when mathematical analysis methods are not available, simulation may be the only investigation tool. I've been saying this many times here, right? I've said this many times, that when mathematical analysis doesn't work because of skill, because of complexity, simulation may be the only real tool left at hand. So when mathematical analysis methods are available but are so complex, costly because of expertise, because of time, because of money, because of effort, the simulation may provide a much simpler solution. And it allows comparison of of alternative designs. Why? Because I created a simulation model, and then I wanted to redesign the system. I create another model for it, and then I can create another model for it, and I can do the comparison in terms of performance. Right? I have one teller machine, and I simulate it. I say too long queue. I can put another model where I have two teller machines. I can run the model on the computer, and I can test. I can add a third one and test. And this testing will help me decide what is the best number of teller machines I need. Here, maybe in actually Albake and these companies are actually using these tools. I think, as far as I know, Albake are using queuing. Queuing. Oh my God. Just. Okay, so they are using these techniques, and that's why if you have noticed, their service levels are very high, because they have designed systems using these techniques. So even with a huge crowd, I remember even in Hajj long time ago, when we saw the queue, we said we'll never be able to get it, but we got it in quite a reasonable time. So there's a huge benefit of using this. So allows time compression and expansion. What does that mean? Simulation allows you to do that, unlike in real systems. Time compression means if I actually have to test what will happen if I add another teller machine, I'll be spending like 3 months, 4 months, right? I have to buy a teller machine, I have to install it, then I have to start recording it. It will take months before I can do that. In Arena, I'll do it like this. I say copy teller machine, run the model again. Even I can run it fast. I'll show it to you in a second. I say run it even fast in even faster mode. The time compression happens, and you don't have to wait. If you're running the simulation for 50 days, that 50 days will pass on Arena in 10 seconds. That's called time compression. But time expansion is if I wanted to visualize what's going on, I want to slow it down. I cannot do it in real world. Something is happening fast. On Arena, actually, there's an option to slow it down. The thing will go very, very slow, and you can actually see, okay, this is where the problem is occurring. Okay, do you understand? So this time compression and expansion are available on Arena. For stochastic model, simulation estimates, not the exact output. It's just, again, we keep on debating about mathematical versus simulation. Simulation are relatively crude outputs. Mathematical are more exact. So it just talks about that. But one of the things that we keep on talking about is the simulation model is as good as the output of simulation is as good as its model. if I have, if in real world this is going on, and what I developed on the screen is something else, and I infer my results based on whatever is going on the screen. Do you think it is valid on what is going on there in the? That's one of the things, inshallah, will be part of our study, is to check for the validity of the model. You know, what you are running on the screen, is it happening on in the real world or not? So these are few things, inshallah, we'll be looking at. I'm not going to go there. I'm going to just show you arena a little bit, and then this is like the whole steps of the simulation study. So we'll be starting with problem formulation, setting objectives, and overall plan. Then we'll be developing conceptual model and data collection together, and then we'll be developing. This is where the arena is. This is where we'll be developing arena model based on conceptual model and based on the collected data. And then I just talked about verification and validation steps. Some of the steps will not do because they are beyond scope. This is like more technical stuff. So design of experiments, and we'll just do it on common sense basis, not on formal basis. And then of course we'll try to evaluate results, and we'll try to suggest improvements in the system and so on. So eventually you have to find a problem where queues are building up, but there's a problem. Like in hospitals or something, you go there are long waiting times. If you go to a place where there's no queue building up, there's no problem, right? You're trying to solve a problem, not just trying to recreate something. So when you're choosing a problem, you need to pick up a problem where either you see or somebody else would tell you that there's a problem. They are having problems with long waiting times and long queues and all those things there, right? So we can first of all develop the model, see exactly if that is going on there, and then we are going to create a solution on our model. And people have done that. So they experimented with different designs, and then they are able to suggest better solution for the companies. Yes. You have to explain me the actual problem. This specific application that we are dealing with, somehow there has to be a queue building up. This simulation cannot help. But again, what you are explaining me, I still do not see a big justification for simulation. First of all, I'll help you. I'll help you with that. Is there something happening over time dynamically? Like for example,
I want to find out certain problems. Like I have my projects are in general category, so I have to do like predictably, like something like that.
No, it's okay. That's how people try to solve problems, right? It comes with brainstorming and visualizing and conceptualizing, which is absolutely fine. Maybe we have to go deeper. How people are shopping. Yeah, so there is another type of simulation which I see something happening to you, which is called agent-based simulation, agent-based modeling, where you kind of it's about dealings and how people are interacting with the system and so on, right? So there's I feel for now that not the simulation, but there's another kind of a simulation which is called agent-based modeling, which might be more useful there. But still, we have to understand the problem better. Understand means at a high level you have explained it, but the actual dynamics of it, how things are working and where exactly you feel that there are problems in which we are trying to capture. Okay, so then we can develop a model according to it, and then we'll try to see if we change this, what will happen if this change, would this help to your customers or not. But it goes into we have to go into the detail to make a best call about what is the best approach. Okay. Now, just quickly to show you how it goes, you can see that again, just like Orange, it has like a drag and drop buttons, right? So I can just drag and drop. So these are again serving different purposes. This is create. These are creating customers. This is like when you have to make a decision, like, when you go into a queue, you have to decide, am I going to be joining this queue or that queue, right? You do that as a customer. If the queue is too long, you say, I go to the other one. So this is like a decision. Then you have what you call processes where the service is happening. By the way, this is just an image on top. Underneath is actually a process. So it's like a fake image on top. But process, you have many other things, right? So, and then you have some performance measures that you're trying to, this is like a descriptive thing. So for example, if I run it like this, let me slow it down. This is called time, you can see time expansion. I've really slowed it down. So this one served very, very quickly, but this one, taking long time. You can see that the customer is deciding to go there, right? Based on the queue. Let me accelerate this a little. Queue building up, right? Now I can experiment with it. If I train my customers better, my service people better, eventually, which would it help? For example, this current waiting time may be acceptable, maybe not acceptable. If it is not acceptable, so the solution could be to add one more lane, or the solution is to train them to speed up the service, right? And then we can experiment. You can see now the queue is building up. Maybe it's unacceptable, right? The queue is reaching, I don't know, I cannot read it well, but it's like in double digits and so on. So again, you can experiment it like this. Let me run this fast, and then eventually what you do is you keep on running it. I don't know if I put a closing thing, but at the end there are reports being generated about performance evaluation and so on, and processes that you evaluate as business people. Then you say, look, this waiting time is too much. No, we cannot allow that. So you have to look at those like results during your projects. I stopped it. I did not let it complete, so it hasn't collected the details about it. But let me try queues. Maybe there are some more information about it. Okay. So waiting time in Q1 was around 12 minutes. This one is 7 minutes. So as a business person, you say, would you mind standing 12 minutes in a queue or on a Hyperpanda counter? You have to make a call. Say, no, it's not what we want. We want people to be served within, let's say, 5 minutes. Now it means there's a problem. You have to solve it. That's how you'll, inshallah, progress to there. So you find a solution, you conceptualize it, you build a model, you run it, you test it, you find what is going on, and then how you can improve it at that. Okay. So I'm going to stop now. I think it's we can go further, but I think it's okay for now today. So next time, because we are dealing with queuing systems, so we haven't learned what makes up a queue. What is a queue? How does it look like? What are the components of a queue, right? So the next class will move away from simulation and we'll go into the mathematical models of queuing. But you'll see that those mathematical models are very nice, very simple. But they are only simple for simple systems. Like the bank example, we gave one queue, one server. But in hospitals and airports, it doesn't happen. Multiple queues coming one after the other, multiple people, very complicated movements, right? So for that, we'll be using simulation. That's inshallah what we'll be modeling. Now I can stop now unless you have a question. All clear? And I think Dima mentioned about bringing the exam script. I just it came to my mind when I was entering the door. My apologies, inshallah, I'll bring next time. I completely forgot about this, and right at the time of entering, I remember that I had to bring the exam paper. Inshallah, next time. Okay. Okay. Thank you. You too. Have a nice weekend.